are calculated by the data access prediction unit. It will be stored in an entry of a history table indexed by the target page and bank ID, which will be provided by a page interleaving mapper. Now, in case the memory controller needs to issue any command or perform any memory operation like read, write, refresh, recharge, or banks, it should first retrieve the value of the counter corresponding to the target bank and page, and based on this value, the DRAM page will be defined as hot, frequently, infrequently. Sometimes we call it like critical performance page or non-critical page. And also the decisions which will be made by the DRAM, by the memory controller, will depend also on where our proposed architecture is utilized or employed. To verify the effectiveness of our proposed architecture compared to the baseline system, we developed VHDL models for the baseline system and the proposed architecture. The table in this slide shows the main parameters that are used by our, in this paper. We built 4 core multi-programming workloads by mixing applications or benchmarks selected from 2 different benchmark suites, Parsec and Media Benchmark. The table on the left side of the slide shows these workloads combinations that are used in our in this paper, while the table on the left side, on the right side of the slide, shows the selected workloads from the Parsec benchmark. It can be seen clearly that these benchmarks have different application domains. This is to prove that the proposed architecture in this paper work efficiently with a wide range of applications that have different application domains. Then the workload combination that are built in this paper are simulated by a GEM5 simulator to capture their memory traces and replay them again on our RTL simulations. As mentioned before, the effectiveness of our proposed architecture compared to the baseline system is evaluated using the accuracy for determining the hot DRAM pages at runtime and the area overhead incurred. No problem. With respect to the experimental results, when running the 4 core multi-programming workloads in our proposed architecture, this figure shows the accuracy for determining the hot DRAM pages at runtime when using history table with different entries size from 16 to 1024 entries. It can be seen clearly in all of the workload combination. The accuracy of determining the hot DRAM pages will be increased or improved as the number of entries increases. Also, using a history table with a few entries, 16, 32, or 64, will provide a low accuracy prediction. Okay, using it can see clearly that the accuracy that using history table with more than 256 will not provide significant improvement in performance. For this reason, as can be seen, this figure also with respect to the, with respect to the area overhead incurred by our proposed architecture in terms of the required storage. This table shows the required storage when using different when using history tables with different sizes, range from 16 entry up to 1024, and it can be seen clearly that, and also the average accuracies that achieved when using, for example, 16 or 32 or 64. The conclusion which can be drawn from this table that the optimal number of entries of the employed history table should be 265 entries, and the accuracy which will be provided in determining the hot DRAM pages at that using 256, it will be 88.1%, and the required storage in terms of bytes, it will be 3080, approximately 3 kilobytes. Now using the cacti, which is area and power memory model, 3 kilobyte will be a negligible area overhead. To sum it up, dynamic random access memory is the main performance and energy efficiency bottleneck of today's computing systems. Several recent approaches are proposed, have been proposed to improve the DRAM reliability, performance, and energy efficiency. The capabilities of these studies depend significantly on identifying the hot DRAM pages at runtime. To this end, for this purpose, we proposed in this paper a high accuracy and low cost hardware-based approach for determining the hot DRAM pages at runtime. Our experimental results when running 4-core multi-programming workloads revealed that 88.1% of the hot DRAM pages were accurately determined using a history table of 265 entries. Using cacti area and power model, the additional 3 kilobytes will be negligible or minimal. Our proposed approach in this paper opens up many avenues for research directions. In the future work, we will examine the possibility of combining our proposed approach with other DRAM optimizing technique that aimed to achieve a high DRAM reliability, efficient exploitation of the raw buffer available at the raw buffer, take the advantages of the capabilities that offered by asymmetric DRAM bank organization, apply the optimal page policy, reduce the negative impact of the raw overfetching problem on the performance and the energy efficiency of modern DRAM systems, and finally map the hot DRAM pages into low latency regions. Also, we will examine the possibility of applying our approach proposed in this paper by other architectures such as tile chip multiprocessor architectures. Thank you for your listening.